Let's demystify transformers. In this video, we will try to understand how transformers work, and then we'll also solve some past questions, some past examination questions based on transformers. Now, have you ever wondered why the sockets in your home, which are usually rated between 220 volts to 240 volts, have you ever wondered why they are able to power your phone charger when connected? Your phone charger requires about 5 volts to get powered on, okay? And then they can also power up your microwave heater, which requires about 2000 volts to get powered up. Now, I'm sure you'll be wondering, will the 220 volts or will this rating not be too much for your phone? Wouldn't it like blow it up? And also, will this 220 volt with this rating not be too small for the microwave, your microwave heater, such that the microwave will not even come on? Now, the simple reason is the presence of a transformer in them. Okay, so a transformer is simply a device that changes the size of alternating voltage. Okay, so it either increases the size or reduces the size of alternating voltage. So for the case of the phone, which requires just 5 volts, it will reduce. So let's say the rating on your wall or the supply on your socket is 220 volts. It will reduce it to 5 volts so it can power your charger. But if you connect your microwave, it will increase the transformer will increase it to 2000 volts so that your microwave will get powered on. Okay, so that's basically how or what a transformer does. All right, so now let's understand, let's just talk a little bit about the structure of a transformer. So a transformer is made up of coils or windings, as they are called. Okay, coils or windings. Now this they're usually wound around a ferromagnet, which we usually call a soft iron core. Soft iron core. Okay, now what really happens is when you connect a device to your wall socket, now the AC voltage, of course, flows in and generates alternating current. Now recall that alternating current is a type of current that changes its direction. So when its direction starts changing, so we have this, so it just goes back and forth, so you can go like this, turn, go like this. So when it's that change in the direction of alternating current generates magnetic field in this coil. Okay, it generates magnetic field in this coil, okay, which in turn will be induced in this other coil here. Okay, so the magnetic flux or the magnetic field will be induced in this in this coil here. All right, and then the presence of the magnetic field or the magnetic flux in this coil then generates current also in it generates of course voltage, which then generates current onto the device and then powers it up. Okay, so that's basically how it works. Now the presence of this soft iron core is to concentrate the magnetic flux or the magnetic field that is produced in this iron core, to concentrate it so that much is not lost. All right, so that it will be transferred to this other coil here. So that's the function of the soft iron core. Okay, we could have more of these lines. Okay, so that's what it does. It just concentrates, you know, the the magnetic field into the secondary, into this other coil. Okay, which we're going to talk about now. So now we refer to this coil here, the input, this coil here from the input, we refer to it as the primary coil. The primary coil. And then we refer to this ones here as the secondary. That's the one at the output, as the secondary coil. Okay, now based on what I said earlier about based on the definition of transformers, where we said it either increases the voltage, reduces the voltage, or increases the voltage. Based on that, we have two types of transformers. Okay, the ones that increases and the ones that reduces AC voltage. So let's look at them. So we have two types. So the first one is called the step down transformer. Okay, from the word step down, you can tell what it does. So what a step down transformer does is, just like in the case of the phone, it steps down or reduces the voltage from the AC source. Okay, for the case of the phone, it reduces it from 220 to 5 volts. Okay, so that the phone can, can be powered up. All right, and then we also have the step up transformer. Okay, from the word step up, it means it increases the AC voltage. For the example we use, it will increase it from 220 to 2000 volts. Okay, so that the microwave can be powered up. All right, so these are the two types of transformers that we have. Now, this symbols here, this parameters here, this here represents the current. IP represents the current in the primary coil. VP represents the voltage in the primary coil, and NP represents the number of turns, we call them the number of turns in or of the primary coil. All right. Similarly, NS represents the number of turns of the secondary coil. IS represents the number of, the current in the secondary coil. And then VS represents the voltage of the secondary coil. All right. Now, how do you differentiate between these two? Okay. First, we've already said that step up, step down reduces voltage, step up increases the voltage. Now, also for a step down transformer, the number of turns of the secondary coil is less than the number of turns of the primary coil. Similarly, for the step up, the number of turns of the secondary coil is greater than the number of turns of the primary coil. Okay, so that's one basic difference between a step down and a step up transformer. Okay, now what is the relationship between the current, the voltage, and the number of turns of a transformer? Now, the number of turns is directly proportional to the voltage of a transformer. All right, meaning that as the number of turns increases, the voltage also increases. Okay, by the number of turns, I'm sure you understand what I mean by all those turns here. We can count them. All right, so as the number of turns increases, the voltage also increases, but the current is inversely proportional, so it reduces. All right, so we can create an equation from this. Now we can say that the ratio of the number of turns of the secondary coil to the number of turns of the primary coil is equal to the ratio of the voltage of the secondary coil to the voltage of the primary coil. And this will be equal to the current in the primary coil over the current in the secondary. Okay, note the difference. This is because we're doing this here, primary over secondary, because it is inversely proportional to this. All right, so this is the relationship between number of turns, the voltage, and the current of a transformer. All right, now another thing you need to note also is that in an ideal transformer, okay, in an ideal transformer, the power in the primary coil will always be equal to the power in the secondary coil. All right, so we can, you remember the power, the primary is referred to as the input and the secondary is referred to as the output. So I can say power input is equal to power output. Okay, and remember, power is equal to current times voltage. So in essence here we can say that the power input, which is the power in the secondary power in the primary coil, will be equal to IP times VP, and this will be equal to the power output, which is the power in the secondary coil, and that will be IS times VS. Okay, so this is another very important equation that you would need in solving questions on the transformers. Okay, now just before we take some examples, before we solve some questions, you also need to note that in a transformer, energy can be lost. Okay, now energy loss in a transformer can be due to certain factors. Okay, it can be due to what we call hysteresis. You'd have to read this up because I'm trying to focus on calculations for this video. Okay, we have what we call hysteresis loss. Okay, you can read that up. We also have heat energy loss rather due to eddy currents to magnetic flux leakage. Magnetic flux leakage. Okay, so you can read them up. Okay, so now let's take a few examples from UTME past questions. Okay, so let's look at this first example. It says a step-down transformer is used on a 2.2 kilovolt line to deliver 110 volts. How many turns are on the primary windings if the secondary has 25 turns? Okay, so this first value here, okay, is used on a 2.2 kV, so that is the primary voltage. All right, a primary voltage, and that's equal to 2.2 kilovolts, which is equal to, multiply that by 1000, so we're going to have a 2200 volts. Okay, that's 1 2 3, yes, that's correct. Okay, then we have this will be our secondary voltage, and that's 110 volts. Okay, so they're asking how many turns are on the primary windings. Okay, so they're looking for the number of turns of the primary coil. All right, that's what we're looking for. And they gave us the secondary, the number of turns of the secondary as 25. Okay, now recall the relationship between this and this. Recall that the number of the ratio of the number of secondary turns to number of primary turns is equal to the voltage of the secondary to over the voltage of the primary coil. All right, so we have all our parameters. We have that will be 25. Okay, number of the secondary, that's 25 over number of turns of the primary, which is what we're looking for, equal to this is 110 over this is 2200. Okay, so if we make this the subject of the formula, I would have NP, number of primary turns, will be equal to 25 times 2200 divided by 110. Okay, so we have that number of the primary turns would be punch that out. That will be 25 times 2200 divided by 110, and that would give me 500. So I have 500 turns. So our answer would be option C. Okay, all right. So quickly, let's look at another example. This one says, if the mains supply voltage of a transformer is this, mains supply simply means, the primary voltage. Okay, so take note of that. So I want to write the parameters at once. With the primary current of 30 amperes, so stated clearly there, IP is 30 amperes. Calculate the output current of the transformer. Output current, remember output is what? Secondary current. That's what we're looking for. If the output voltage is as Vs, okay, if Vs is 450 volts, okay, so we're looking for Is. Now recall the relationship between this and this. Remember, they are inversely proportional. So Vs over Vp will be equal to Ip over Is. Take note from the equation we generated. All right, so let's slot in our parameters. Vs is 450 over Vp is 200 equal to Ip is 30 over Is is what we are looking for. Okay, so now if I make Is the subject of the formula, Is will be equal to 30 times 200 all over 450. Okay, so let me punch that right into my calculator. So our current in the secondary coil will be 30 times 200 divided by 450, and that's exactly our Is is exactly 13.33. 13.33 amperes. And that's option A. Okay, so that's it. So if you have any questions, you could drop them in the comment section. I'll be glad to answer them. Please subscribe to my channel. Thank you.